Hey guys, my name is Jani. Welcome to the Optofidelity Test Corner. Today we are starting a new series of episodes concerning waveguide displays. We will start from the basics and then we will dive a little bit deeper into the subject. I have here Product Manager Joonas Pylväinen from Finland. Welcome to the show.
Thank you very much. Thank you for inviting me.
Yeah, so Joonas has been working in Microsoft in his previous life, and he has been working with HoloLens, and he has a lot of understanding and knowledge on waveguide displays that are used in the HoloLens product. So, Joonas, I was thinking that we could start first from the beginning. Why do we use waveguide displays? Why not, for example, LCD or OLED or micro LED or something like that in front of your eye, and that's about it?
Well, that's a good start actually, but firstly, in the past, of course, these traditional displays haven't been transparent at all, which is the kind of the first blocker that has been there. But nowadays, of course, we do have transparent OLED displays that are being used in televisions and kind of these bigger equipment, or even transparent phones that have been conceptualized at least. But the main issue there is that with the kind of flat panel, you always need, even with the transparent one, you always need kind of additional optics in front of the display, because you need to be able to focus the image on a distance, because otherwise the image will be directly on your face and you cannot make out what the image is about. So that's, for example, if you think of these traditional headsets like VR headsets and these non-see-through headsets, they have a lot of they have an optical stack in front of the display itself, basically.
Yeah, so basically if you would have AR device that would use traditional displays, it would look even thicker than a bottom of your beer bottle. So you wouldn't really like to have something like that stuck to your face.
Exactly. Of course, the technology there is going forward as well, that the optics there are getting flatter and flatter, but still not kind of a eyeglass form factor capable.
Yeah. And then just to clarify a little bit to the audience here, so in the previous episodes we were looking at the Apple Vision Pro device, and that is called mixed reality device. So it basically has cameras outside, pointing outside the device, and it is showing you the real world through the cameras and then with the traditional display. But then when we are talking about augmented reality devices, there you can actually see through the display. So you can see the real world without the cameras, and that is a big plus in AR applications, because then you don't need to worry about latencies or anything like that. So basically just overlay the image on top of the real world. So that's kind of the difference between this mixed reality and then the augmented reality devices. But yeah, let's go a little bit deeper then on waveguide. So then what is a waveguide display?
So waveguide display is basically a display or a flat display made out of optical elements that are meant to direct the light to a specific location. For example, you have in a simple waveguide, you have one optical element that incouples the light from the projector, then the light propagates within the waveguide, and then you have a second optical element that outcouples the light to the user's eye. So that means that you can have this kind of a flat display, and you can propagate the light from a different place into the user's eye, so the user doesn't see the projector at all in this case, and can have the transparent display, as you said.
Okay, so then you would be able to make devices that look like normal piece of like eyeglasses or sunglasses, basically.
Exactly. And in those cases, you probably would have the projector maybe on the sides of your head on the temple side, and you would propagate the light towards your eyes and then out couple it from the display into your eye. So.
And then I understood that there's kind of two ways to do this. So you can have the light coming from the same side as the eye, but also from the opposite side.
Exactly.
Your eye.
Exactly. Those would be the kind of two different modes that you can have. So first is kind of a mirror mode or reflective mode of the waveguide. So basically it means that we have the waveguide and we are incoupling the light from the same side that it's outcoupling. So it is mirroring. Then the other one, the transmission mode, is where we have the light incoupled from the other side and it comes out from the different side. So it would mean in a headset that your projectors are, instead of pointing outwards, they are actually pointing inwards here, so you can see the light.
But it kind of sounds like it would be more logical to have always the one that is kind of like on the same side. That is, if you think about where the projector would be like next to your temple here, and then your eyes basically on the same side then as the projector.
Yeah, that would make the most sense kind of form factor wise to have it on the mirror mode.
Yeah. And then how about the angles? Like which angle then the light comes out from the waveguide? Does that have some special terms or something that people are using?
Indeed. Of course, it's also kind of a design choice that what you are looking for. But commonly, the terms that are being used are pantoscopic tilt and phase wrap. So pantoscopic tilt meaning that you have the waveguides here and you are tilting them towards your face or outwards, usually towards your face. And then with the phase wrap meaning that you are either going inward or outward here. At least for the tilt part or the pantoscopic tilt part, one reason is that the human eye naturally gazes downwards a bit, so we are not looking at 0 degree angle. Usually we are looking a bit downward, and depending on the study it's some degrees, 5-10 degrees, something like that.
Okay, so basically however you design your device, like how do you want to have those lenses tilted and then how you like your device to look then basically you will try to choose those angles accordingly.
Exactly. So partially a design choice, partially also kind of made for the human experience or how human eye works.
Yeah. So then something that I'm sure that the audience is now wondering, like how do you make the light go inside the glass and then come suddenly out from the glass? So what is the technology there?
So the technology or the magic there is that we have different kind of nanostructures, for example, on the glass, and let's say on the incoupling optical element, the purpose of the structure is to incouple the light within the glass. And when the light is within the glass, it will travel forward with the total internal reflection until it reaches the optical element which is meant to outcouple it. Of course, there might be other optical elements in between as well, so it might not be just the incoupling and outcoupling, but something in between as well.
Okay, so these optical elements that then somehow bend the light into the glass and out, what are those?
So, depending on what type of a waveguide we have, for example, these kind of typical, or let's say 3 common most three most common waveguide types are diffractive waveguides, holographic waveguides, and reflective waveguides. And the first two of them, so diffractive and holographic, they are based on the kind of a mechanism of diffraction. So when the light hits the structure, it is diffracted into the waveguide, where it then travels with the total internal reflection. And in the outcoupling element, again, the diffraction outcouples the light to the user's eye. Now with the reflective waveguides, in similar fashion, there is an incoupling element, an outcoupling element, but instead of diffraction, the light is moving there by reflection, as it already in the name of the waveguide technology.
Yeah, so something that would be easier for people to understand is most likely this reflective waveguide. So is that basically like a mirror?
Basically like a mirror, but instead of being like this, let's say, a mirror in your house, it is kind of a partly reflective only. So it's partly transparent, partly reflecting. So if it was a regular mirror, you wouldn't be able to see through the glasses again. But at the same time, you need to make the light travel forward, but at the same time, you need to also see through the mirror. And of course, when we are talking about waveguides, it's just not usually one mirror, but there's multiple mirrors in an array.
So basically, to put it into like a layman terms, is that you would have, it's a little bit like a periscope. So you have a mirror that basically points the light inside the glass from the projector, and then you have these like half reflective mirrors that are pointing the light back to your eye.
Yeah, indeed. I'd say that's a good kind of overall of that how it works.
Yeah. So then I guess things get a bit more complicated when we start talking about these diffractive and holographic waveguides.
Indeed, yes. So instead of having mirrors, we have nanoscale structures on top of the glass, and in the case of diffractive waveguides, those structures are usually these surface relief gratings, so SRGs. So there is a pattern, or let's say a structure made on top of the glass for each of the optical elements, and those are diffracting the light as per design. And now with the holographic waveguides, instead of having these surfaced structures, the kind of the holographic design itself, it's recorded within the material itself. So instead of having like a distinct structure, there's usually kind of different modulation of the refractive index within the material, and that causes the light to diffract inside the waveguide. So those are the two different kind of diffractive or diffractive mechanism waveguides we have.
Okay, and then when we are talking about diffraction, that probably means that we are in a fairly narrow wavelength range. Indeed.
Of course, depends on the design as well, but usually the diffraction is on the pretty narrow wavelength scale, or if it supports many wavelengths at the same time, there is certainly some trade-offs bound to happen.
Yeah. So now we kind of went into the subject of the differences between these different types of waveguides. So what are the major differences? Like, why would you choose diffraction instead of reflection, for example?
Well, first of all, I think the diffraction and holographic waveguides are a bit further in the kind of a technology path. So even though at the moment they have kind of lower efficiency, maybe some issues in the color uniformity, they can still reach pretty good field of view and a large eye-box as well. So eye-box being the term used for the area where you can actually view the image shown in the augmented reality glasses.
Oh, this is actually a good point. We didn't yet talk about this eye box. so basically what you are saying is that when you have your eye on that eye side of the waveguide, there is a certain area that your eye can be and you can still see the full image. But when you will go away from that area, the image is kind of lost. Is that correct?
Exactly. Or it could be that the eye box is very large, but the image quality is changing a lot over the eye box as well. So you can technically see the image, but the quality might go down as well.
Okay. But then I guess the eye box, or we would like to have the eye box fairly big so that many people would be able to easily use the device without constantly adjusting it or keeping their eye always like in a fixed position or something like that.
Exactly, that's a very important feature as people have different IPDs, so interpupillary distances, so they vary quite much. So that's important that you can cover all the customers or all the users you have. Another thing, of course, is that if your eye box is very kind of limited, it also means that the user needs to align their eye pretty accurately there. Even though they would have the perfect eye distance for your product, if they need to use a lot of time to align it perfectly, that even if you walk around, you might be, moving in the eye box and the quality might change.
Yeah, so then definitely the usability of that kind of device would not be that great if the image is all constantly changing.
Exactly.
Okay, good. Now we covered this eye box, so let's go back to the original subject. So why would people choose like reflection versus the diffraction?
So we covered a bit on the diffraction already. So being there, the efficiency is a bit on the lower end, and the color uniformity is challenging as well. But on the other hand, the kind of manufacturing technologies are pretty advanced already, and the designs are reaching that you can have like a single plate or single piece of glass where you have all the colors, so RGB, red, green and blue. However, that one also has the limitations that usually again the efficiency is lower and the field of view might be a bit limited. So to kind of capture a bigger field of view and have all the good kind of qualities there, you would need to make the waveguides color specific. So in the minimum case, it would meaning having 3 waveguides stacked together, so red, green and blue specific waveguides.
So basically when the diffraction is limited to such a narrow range of frequencies in light, then you can only use like really precise colors on each waveguide, and then also you can only use really limited amount of light. Instead of having the full spectrum of white, you only can use like really narrow spectrum, for example from the green or then the red and the blue.
Exactly. Of course, this is a design choice that we are getting further there, that we can support everything in one, but it's a trade-off, of course.
Yeah, and I guess things get really complicated when you start adding more colors in one design.
Exactly, the designs are getting complex and also the structures are more complex.
Yeah. So then how about when you have the reflection, and that is basically a mirror? Does it mean that kind of waveguide can use all the colors on the spectrum?
Well, basically, to put it simply, yes. So the color uniformity there and also the efficiency is much better compared to the diffractive or holographic waveguide. But then the challenge comes there that since you are making reflections there, spreading the image around or making it a large field of view is limited by the size of the mirror, of course. And when you increase the size of the mirror, you are also increasing possibly the thickness of the waveguide itself. So it might be much thicker than a diffractive waveguide.
And then how about the manufacturability of these two technologies?
Well, of course, with the diffractive waveguides, the accuracy required for the gratings or the surface relief gratings is quite demanding. They are very sensitive that you can replicate the design well enough so you get the expected results. But you can already mass manufacture them, or let's say in a lower volumes mass manufacture them. Then on the reflective waveguide side, the challenge is of course having transparent material, coating that transparent material with some mirror-like or half mirror-like substance, having it uniform so it doesn't cause any kind of image quality defects. So that's a challenge. And then of course, if you are stacking these layers to kind of create the array of mirrors, you need to kind of design that very, very carefully how you do the stacking, and then you need to do cutting or slicing of the stack, which of course is a mechanical process, so it can cause problems as well.
Yeah, it sounds like in the diffraction side, you basically just kind of print the structure on the glass, which sounds like that could be done really easily for many waveguides at the same time. But then if you think about those mirrors, you actually have to mechanically make those mirrors, so you can't just easily just mass produce them in one, like let's say one wafer. You actually have to make every individual waveguide separately.
Indeed.
Okay, so yeah, that's a big difference that if you think about like the UPH of making these parts.
Yeah, it's a thing to take into the consideration. Of course, again, in both sides or in both diffractive and reflection, the manufacturing technologies are advancing. So the diffractive ones have been on the market or in kind of existing products like the HoloLens a bit longer, and the reflective ones are just coming to the market, so there's still development there to be done.
Got it. Okay, thank you, Joonas. I think this will conclude our first episode. We now covered the basics of waveguides and also what are the differences between different waveguide types. In the next episode, we will talk a little bit more about the design. So yeah, please guys, stay tuned. What's the next episode? And we'll see you there. Thank you, Joonas.
Thank you very much. See you later.